In the first lecture, we are going to see my development environment and we are going to write a simple C++ program and execute it. Here you can see that I am using Ubuntu 18.04. Also, for compiling our C++ files, we are going to need a C++ compiler. For the most part of the course, we will be using G++ compiler. As you can see here that I don't have the G++ compiler pre-installed. So we will install that first. Now we are ready to write our first C++ program and execute it. In our first program, we are going to take two numbers from the user and then we will display the results of its addition and division. We will create a folder on the desktop called CMake tutorials. In that folder, we will create another folder called module 1. In this module 1 directory, we are going to create an empty C++ file. Let us name this file main.cpp. Let us open that file and write the code. Once we have completed the coding part, we will compile the program using G++. This command is going to generate an executable called calculator using main.cpp. Let us run the executable file. We will provide the two numbers here. As you can see that the results are correctly printed. Now let us edit main.cpp to make this file a little bit more modular. Here I am going to write three different functions. The first function will do the addition. The second function will do the division and the third function will print the results. Let us modify the code accordingly. Now we are going to compile the code and run the executable. Here you can verify that we are getting the expected results. Now let us move one step further. Instead of writing all the functions in main.cpp, we can have three separate files for three functions. Let us create these files addition.cpp, division.cpp and printresult.cpp. Now we will cut the function definition from main.cpp and paste those in respective files. At this time, if we compile the main.cpp, it will give an error. The error message says that these functions were not declared in this scope. To resolve this error, we need to declare these functions in main.cpp. Now if we compile this main.cpp file, a new error message shows up. This error means that the linker cannot find this function's definition. So we need to tell G++ where is the function definition. To resolve this error, we need to specify the other C++ files in the G++ command, like this. Now we can see that the executable is generated and we can run this executable successfully. Coming back to main.cpp here, we declared the functions inside main.cpp. Instead, a recommended way is to write the functions declaration in separate header files and thereafter include those in main.cpp using #include directive. We will make these changes in our project before we move to the next lecture. In the next lecture, we are going to understand how G++ generates an executable and the problems associated with it. Also, we are going to learn the recommended way to solve these problems. Thank you. Hello. In the last lecture, we compiled 4 different C++ files using G++ command. When we are compiling a project containing multiple C++ files, initially, all the files are compiled independently from each other. In our example, the 4 C++ files were compiled to produce 4 different compiled binaries. When compiling main.cpp, all you need to tell the compiler that 3 functions used in main.cpp do exist somewhere. We have done that by including header files, which contains the function declaration. At this point, the compiler does not care about this function's definition. During the compilation process, the compiler places a placeholder where the functions are called. These placeholders tell that the function call will be resolved during the linking process. During linking, the linker finds the compiled binaries of addition.cpp, division.cpp, and printresult.cpp and links those all together to produce one single executable. One thing to note here is that as long as you have the header files containing the function declaration and the compiled binaries of C++ files, you will be able to build the project. You don't need the C++ files containing the function definition. The example explained in this lecture had just 4 files, but in the real-world project, sometimes the number of files in a project might go above 1000. In such cases, it's a very challenging job to keep the track of all the files and its dependencies. Also, the compilation process in such projects takes a lot of time, sometimes more than tens of hours. Therefore, if the dependencies are not very well managed, every time we modify even a single file, we need to compile and link all the files from the beginning, which is a very time-consuming process. In such case, if we have access to a tree-based representation of all the dependencies and a list of files that we have changed since our last successful compilation, then we can choose only to compile the files that we have changed recently, and thereafter we can link all those together. This would save us a significant amount of time, since very few files are changed in one go. This is where the build system comes in. You might have heard of Make, Ninja, and Gradle or any other build system. These build systems are softwares for automating the source code compilation and linking process. Opting for one particular build system over the other is sometimes a matter of personal choice, where sometimes it is restricted by the development environment. In the coming lecture, we are going to build our project using a popular build system, Make, and have a glimpse of something called Build System Generator. Thank you. Usually, for building a project, the developer writes a special code in something called build files, which is different from the project's source code. And then the build system uses that build file to compile and link the source codes. In case of Make, the developer writes a Makefile and runs that code using Make build system. For our example, we will create a Makefile in module 1 directory. Note that the name of the Makefile is case sensitive. Now we will write the rules in Makefile. You should not be concerned about the contents of the Makefile as of now. If you want to, you can download and understand the Makefile from the download section. Now let us run the make command. As we can see that the make tool is not installed in my system, so we need to install make from the repository. Once installed, we will run the make command. The make command is going to look for a Makefile and then build the project based on the rules written inside Makefile. The output of this step is an executable. Notice here that it is compiling all the files and then linking them all together. Now let us change one of the files and run the make command again. Notice here that the make command has only compiled one file, the one that we have changed just now, and everything else is linked thereafter, thereby saving our time. The idea here is not to teach you about the make files or build system in general, but about the meta build system CMake. The CMake tool is capable of writing the make files for us. Now the question arises, why do we even need to learn this new tool CMake for this simple application? The problem is that the building of C++ projects is not standard across the platforms. This means even if you have the source codes and makefile of a C++ project from your Linux machine, you cannot directly build that code inside Windows operating system. Similarly, if you have a Visual Studio solution from your Windows machine, you cannot directly build the project in a Linux environment. CMake solves this problem by creating the platform-based build system files. Before moving forward, let us delete the compiled binaries that the make command has created. In the coming module, we are going to have a look at CMake tool basics, and then we are going to generate a makefile for our project using CMake. Thank you. Hello and welcome to the second module of this course. In this module, we are going to learn how to install the CMake tool, and then we will write our first CMakeLists.txt file using the most popular CMake commands. There are three ways to install CMake, and we are going to see all these installation processes one by one. The first method is by installing CMake from the repository. You can run sudo apt install CMake in the terminal for this. We can check if CMake is installed properly by running CMake --version. If you are getting an error, it means CMake is not properly installed. Here we can see that the CMake version is 3.10.2. Before moving to the next technique, we will uninstall CMake. The second option is to download the compiled binaries from CMake's official website. Here you can see that the latest released version is 3.16.2. In the download page, we will go directly to the binary distribution section and download the file corresponding to Linux. We can download either of these files. Here we will download the .sh file, which is a shell script. Now we will go to the download folder. Open the terminal from the download folder and give execution permission to the script using chmod +x command. Then run the script. Here we can see that a folder is created. If you choose to download the tar file and run the tar xvf command, it will also result in the same folder. Now, once we have the folder, we can go inside the bin directory. Here we have the CMake executable. To use this executable, we need to add the path of this executable to the system path. We can paste this command in the .bashrc file inside the home directory. Here I have added the path and we can see that CMake ---- version is giving us the expected output. Before proceeding to the third technique of installing CMake, we will remove the previously downloaded files and the bashrc entry. Now, we will download the source codes from the CMake website. Now, extract it using tar command. Once extracted, we can navigate inside the directory and run these three commands. After running the bootstrap file, if you are getting an error, you should run this command also. This process took around 5 minutes in my computer, so I am forwarding this video. Now we will run the make command, and lastly we will run sudo make install. After a successful installation, we can check the CMake version. As you can see that the CMake has been installed properly. Once we have the installation, we can move to the next lecture. Note that in this course, I have used CMake version 3.16, which I installed from the source. For you to follow along, any version greater than 3 is fine. In this lecture, we are going to see the basic setup required for using the CMake tool. When we are running the CMake command for the first time, it needs two information: the location of CMakeLists.txt file and the directory location to store the build system files. The CMake tool finds the CMakeLists.txt file, processes the information written inside it to generate the build system files in the specified location. A common practice is to have the CMakeLists.txt file in the top level project directory. The build files are kept inside a separate subdirectory of the project. Note that the folder name for storing the build system files could be anything, but the name of the CMakeLists.txt file is fixed. If you rename the CMakeList to anything else, the CMake will give an error. Firstly, we will copy the folder from the last module and rename it to module 2. Now, we will remove any executable, compiled binary or makefile from the previous session. Now, let us create a folder for storing the build system files called mybuild.dir. Also, let us create an empty CMakeLists.txt file in the top level directory of the project. The top level project directory is module 2 here. Now, we are ready to run our first CMake command. We will navigate into mybuild.dir and then run the CMake command using double dot argument. Here, double dot argument tells CMake that CMakeLists.txt is inside the parent folder. Also, by default, CMake generates the build system files inside the directory from where the CMake command was executed. In this case, the build system files are going to be placed inside mybuild.dir. Now, let us run the CMake command. As we can see that the command is executed successfully and the build files are generated inside mybuild.dir. If you do not have G++ or GCC compiler installed in your system, this command is going to fail. In such a case, install these compilers to get rid of the error. Now, let us have a look at the build system files that CMake has generated. Out of all these files, Makefile and CMakeCache.txt are very important ones. This Makefile is used by the Make tool to build the project, and the CMakeCache.txt is used by the CMake in the subsequent runs of the CMake command. Running make command will not generate any executable as of now, because we don't have a source code to make that executable. Note that we always run make command from the folder which contains the make file. In the next lecture, we are going to populate our CMakeLists.txt file to generate an executable. In this lecture, we will generate an executable using CMake and make commands. Firstly, let us delete the build files from the last session to start afresh. For that, we will navigate inside mybuild.dir and remove all the files. Now, we will edit the CMakeLists.txt file. The CMakeLists.txt file consists of the commands required to build the project. These commands are executed one after the another like a script. The first command we will learn is add executable. This command is used when we want an executable file at the end of the build process. For successful execution of this command, we need to provide the names of the final executable and the source files required to build that executable. We will name our executable calculator, and the source files required for this executable are addition.cpp, division.cpp, printresult.cpp, and main.cpp. Note that the naming sequence of all these source files do not matter, but the name of the executable should be the first argument. Here we have our CMakeLists.txt file ready, and now we can execute the CMake command from the mybuilddir directory. We can see that the command executed successfully with just one warning. In mybuilddir, CMake has generated the Makefile for us. Now we can run the make command to generate the calculator executable. Here you can see that our executable is generated. Let us execute this executable and verify the output. Now let us resolve the warning that we got. Every CMake project requires a name for the project. To resolve this warning, we need to specify the project name and an optional version number of this project. We will do that using the project command. Apart from this, it is a common practice to specify the minimum CMake version in the CMake list file. If the CMake list file is using any feature from a newer version of CMake, then you might get some mysterious errors if you have an older version of CMake installed in your system. By specifying that minimum version, we are telling CMake that all the features used in the script is supported by that particular version. You can use the command CMake minimum required to specify this. At this point, if we copy these files to another system with an older CMake version, the CMake command will fail. As a developer, it is my duty to test the script with an older CMake version and mention those numbers here so that the maximum number of people can use this project developed by me. Now we can run the CMake command and verify that the warnings are gone. Coming back to our CMake list file, we have specified that these 4 files are used for making our executable. Now at this point, if we change just one file, say divide.cpp, and again execute the make command, we can see that only divide.cpp is compiled, and then everything else is linked altogether. Although we have been successful in generating the first executable, there is no sense of hierarchy here. Which means anyone reading these lines of code would not understand whether main.cpp is depending upon addition.cpp or addition.cpp is depending upon main.cpp. This might create a problem when managing the large projects. In the coming lecture, we will make the project modular with some sense of hierarchy.